So today I want to talk about the different ways you can produce gravitational waves from stellar collapse. We're now at the point where we're looking at things that we don't have any data on yet, but we hope to have data sometime maybe before people like Friedel and I pass away. I had to at least make fun of your age at least once, Friedel, during my talk, so here we are. So Einstein came up with a theory for general relativity, and his observational, so he wanted to test this theory. So the data that he was actually trying to fit was the perihelion precession of Mercury. And because we just passed the 100 years of relativity date, there was a lot of museums, shows where you could see information from Einstein sending his text around, trying to get it tested. And he had sent something to Michel Bessel. And he had done this derivation, a nice detailed derivation of what the perihelion precession should be if his theory of general relativity was correct. He had gone through the math, and it turns out that that perihelion precession went as m squared. And he plugged in numbers, and he was off by a factor of 100. And they actually, and I wish I had gotten this picture to show you, but he'd gone through all these derivations, and there was a plug-in of the mass of the sun. So he'd done all the detailed calculations, plugged in the mass of the sun, and his mass of the sun was 2 times 10 to the 32 grams. And not surprisingly, he was off by a factor of 100 in his result. Michel Bessel actually caught it, sent it back to him, and fixed it. So the first pass at doing the calculation, he did not fit this, but when he actually plugged in the right mass for the sun, he got the perihelion precession for Mercury. Not long after, Eddington made a trip to go look at the solar eclipse where he could then see the lensing of the bending of light. And so this was the confirmation. This was the data he knew and he was just predicting. This just matching. So he was post-dicting this data. He predicted this bending of light, and that really started to turn the community to believing in this theory of general relativity. We now see a lot of gravitational lenses, and I know a lot of you know more about this than me, but at this point, people have understood and believed general relativity. The next step is the emission of gravitational waves. And so if you think of general relativity is matter telling space how to curve, and then space tells matter how to move, you have this, this is the kind of standard picture where people show a curved space-time through general relativity. Then the objects are actually following geodesics around that curved space-time when you get their orbits. If you make the simplest picture of how our gravitational waves produced is if you change that space-time rapidly, you have to have some way of signaling that that change of space-time is occurring, and that change in curvature, and that's what gravitational waves send us ripples out in space-time with that information that something is moving. So this is gravitational waves. The history of trying to detect gravitational waves starts really with Joe Weber. His idea was to build a really big cylinder of material and then look for the vibration. So when the gravitational wave passes. So curved space-time moves through it, it'll vibrate this big cylinder. In his case, it was big aluminum cylinders. It would vibrate them, and those vibrations, he would detect them, and with that detection, detect gravitational waves. These are not that sensitive. He did claim to have detected supernova 1987A. People did not believe him. The gravitational wave signal would have had to be very strong for his detectors to detect it. But he did kind of set the tone of what we could possibly do with detecting gravitational waves in the 60s. In 1962, Michael Gertzenstein and Vladislav Pustovoit, I can't even say these names, proposed using interferometry instead. They then independently was proposed by Joe Weber and Rainer Weiss in 1967. In 1970s, Kip Thorne, Ron Drever, and was it Paul Whitcomb, formed an experimental group to start planning seriously to detect gravitational waves. Ray Weiss joined this team, and it ended up becoming Weiss, Drever, and Thorne, pushing forward what in the end became the LIGO detector. So I'm being a little bit LIGO-centric here. Well, a lot LIGO-centric. So here are the LIGO observatories. There are two interferometers, two sets of interferometers, one in Livingston, one in Hanford. The third set of detectors is being shipped right now to India to make a LIGO India. So they're long interferometers. The way the interferometers work for detecting gravitational waves is the simple interferometry you might expect, where you have two long pipes. You're letting light bounce back between these mirrors, and then you're letting them combine. If they are in tune, their signals will add, or they'll cancel each other out. You can test that subtraction or addition. You can test any motions. If a gravitational wave comes through, it will affect the length of this bar different than this bar, or this line is more than this line, and you'll get that interference, and then you'll see the signal. So that's what they're trying to measure. They're trying to measure something at the level of 10 to the minus 22 and change, so they have to be extremely accurate. It means that the test masses that they're using, the mirrors that are hanging, all have to not shake. And you'll see when you look at the LIGO sensitivities, the shaking of the mirrors puts in definite noise into the detector. But they can do this interferometry, and in fact, this is what they kind of did with the initial LIGO. Here's the initial LIGO detector. They said, we're going to try to get this kind of sensitivity right here. This white dashed line that's going up like this. This is the sensitivity they wanted to reach. They ended up working on their detector and eventually got down to this sensitivity. So with the initial LIGO, it was a little bit better than 10 to the minus 21 for the lowest sensitivity. These lines are, a lot of these are wiggles in the fact that the mirrors oscillate just a little bit, and that small oscillation causes these line signatures and this noise. So they beat down the noise as much as they can. They demonstrated that they could get displacements of 10 to the minus 19 meters, and so they can show that this technique worked. With that, they got extra funding to build advanced LIGO, and that's the state we're at now, where they've then they've gone through all of the parts of the detector, improved them in several different ways, and the sensitivities that they're at right now are this blue curve. They're trying to beat it down, so they're not, I could not get them to give me a straight answer as whether they had gotten to what they wanted to have in the second science run, this green curve. But this is the sensitivities that they were at last I talked, and they were struggling to get the green curve sensitivity. But it's not, it's something, it's an engineering problem. They have engineers that have a lot of training on this, so they do think they're going to beat down to eventually this sensitivity that's going to be below 10 to the minus 23 in amplitude. I want you to keep these numbers in mind. Right now they're detecting at about 10 to the minus 23 at frequencies of about 100 hertz. So the frequencies are important for supernova. This is, you're looking at things where the sensitivity is best at around 100 to kilohertz. So you're looking at millisecond periods. When you're looking, so 10 millisecond to 10 millisecond periods, that you're looking for whatever kind of motions you have. This really does push you into things like supernova, where you have something going down to a compact object. It has to be a compact neutron star or a compact black hole to get strong signals. If you wanted to get a signal that was, you cannot detect really large black holes in this because they don't get these high frequencies. So LIGO is limited to high frequency gravitational wave signals. White dwarf mergers are also too low frequency to be detected with LIGO. This is what LISA is designed to detect, but these ground-based ones are focusing on the high frequency. Now there are more than just LIGO detectors. There's the geodetector Virga, the Japanese detector, and I think the LIGO is still in place to be produced in Australia. There will be one version of LIGO being moved over to India, so there should be a third LIGO detector in India. And with these, we get a lot of these detectors increase the sensitivity a little bit beyond what LIGO can do, but they also are making a broader lever arm so that you can get better positioning with the LIGO with the detections of gravitational waves. The Japanese detector is actually being built deep within a mine, and they use it they're essentially going to be testing a lot of the new technology for the next generation gravitational wave telescopes. GEO was also used to test a lot of technology, so they've been both testing new technology and developing more gravitational wave detectors with time. So the number of gravitational waves, the potential for gravitational wave detection is just increasing with time. What I want to spend most of this lecture on is actually how we calculate gravitational wave emission and what we can learn from gravitational wave emission in core collapse supernova. So to get it out, there are simple formula or somewhat simple formula to get the amplitude for gravitational waves. It's looking at the second derivative of both the mass and current quadrupole moments in your source. You can see that it goes down as 1 over the distance, so better than electromagnetic radiation as far as seeing things at far distances. It only falls off as 1 over the distance, not 1 over the distance squared. So the amplitude is not getting weaker as quickly as it is for electromagnetic radiation. And it's because we're measuring the amplitude, not the power. So you typically in your codes, you do something like this. You discretize the quadrupole moment. So you take whatever your information is, and you can just, if I was doing a particle method, I would just take the density at different coordinate points and just sum them up, integrate them up, and get a solution. I can plug this in, and it's easy to calculate the amplitude as a function of time. For gravitational waves from supernova, people have classified them into a few different categories where there's, depending on the rotation of the collapsing core, if you have mild or no rotation, the kind of signals you'll get are either from that turbulent mixing in the engine or from the rotating core making a quadrupole moment that is changing with time. If you can go to higher angular momenta, you can get more interesting signals. You can get bar modes. You can fragment when you collapse. For protoneutron stars, you can get R modes on the rotating neutron star. So these are Rossby modes. We'll go into detail on them. And there's also black hole ringing. When you accrete onto a black hole, you actually change its metric, and you can cause it to ring. I'm not going to talk about it much, but there's also asymmetric neutrino emission that can give give a gravitational wave signal. So these can happen not just in supernova, but things like the accretion-induced collapse of a white dwarf down to a neutron star. When you have fizzles or the very massive stars to collapse, you can also form gravitational waves through this black hole ringing. So there's a lot of ways you can produce gravitational waves. This is what I'm going to spend the first bit of the lecture on. This is what the likely signal is going to be. So this is what we're probably going to get from gravitational waves, and then we'll go on and discuss what are the potential for other signals if we increase the rotation of the stars. So in a simple supernova, we again come back to our picture. I have my protoneutron star, I have material accreting, and I have mass motion as this convective turnover is happening. It is that mass turnover that can give us some idea of what, some gravitational wave signal. That's a quadrupole moment. It is changing with time. So it's changing, and its second derivative is changing. So I have a non-zero acceleration on the quadrupole moment, and that will end up producing a gravitational wave signal. So here's some calculations of this. This is by Jeremiah Murphy and company. And you can see here's that amplitude. Here he's multiplied times distance. So he has the amplitude times distance, and here's the signal that he's expecting. And then as he starts to drive an explosion, it moves off. But this is the signal that he expects. And he argued that he could predict things like the position of the protoneutron star, the position of that convective region, just by looking at this gravitational wave signal. I will point out that the signal that he has, so it's h times the distance. So if we remember the sensitivity of advanced LIGO, when it gets to its design sensitivity is going to be about 10 to the minus 23 in this strain. His sensitivity is, if I divide by a distance of, say, 10 kiloparsecs, so 10 kiloparsecs is roughly 3 times 10 to the 22 in distance. If I divide by that, you're looking at a strain of about 10 at 10 kiloparsecs, a strain of about 10 to the minus 22. So 10 to the minus 22 from this convection. The design specificity of advanced LIGO is 10 to the minus 23. You'd have a pretty good signal if the supernova went off 10 kiloparsecs away. I think you would have trouble going out to 100 kiloparsecs. That's the kind of size scale you're going to be able to see these gravitational wave signals. So we're looking for in this particular case, we're looking for a galactic supernova. Several groups have done this kind of work. Chris Donat found that by including the core, he can get higher frequency signals compared to things like Muller et al. In 2012. But again, the signals they're getting are on the order of 10 to the minus 22, a little bit less than 10 to the minus 22. So advanced LIGO will be able to see it, but you're looking at something that is not, it's only able to see it if you are 10 kiloparsecs away. So we're looking at distances of 10 kiloparsecs. The problem with all these calculations is that we're still far from resolving the turbulence. So we don't have, I don't think we're predictive in how this signal will look like. The good news is we will get a signal and it'll tell us things, but I think we don't know exactly how its behavior will be. We don't know the seeds that are driving the convection initially, so we don't know how that evolution is perfectly. And then we've also discussed a lot of the details of the convection and the explosion depend upon uncertainties in the microphysics, like the equation of state and the neutrino transport and the magnetic fields. So lots of groups have done this. Here's another set of calculations. Again, here's in the at 10 kiloparsecs signal, what the signal is times 10 to the 22. So this would be 10 to the minus 22. These are different explosions with slightly different conditions. The signal changes, the amplitude changes some, but it's all on the order of about 10 to the minus 22 or less, or 5 times 10 to the minus 23. So we are agreeing on that kind of signal. The signal is between about 5 times 10 to the minus 23 to 10 to the minus 22 for a supernova that goes off within 10 kiloparsecs. So this is going to be something that we will only see with a galactic supernova, even with advanced LIGO working at design specificity. So you can get signals in different ways. We can go back and look at the things that we were invoking to drive kicks. You can have an asymmetric collapse. Remember, if the convection in the star is turbulent before it collapses, it can be slightly global asymmetries. Those asymmetries, when they collapse, they produce asymmetries in the explosion. That asymmetry can maybe perhaps drive a stronger signal. So the signals for this, here's some different asymmetric collapses, and instead of 1 times 10 to the minus 22, you can get 8 times 10 to the minus 22 signals. So you can get almost an order of magnitude higher in some cases. In some cases, it only gets a factor of 2 higher. But these asymmetric collapses can cause slightly stronger signals. And I think the real thing here is so that doesn't really help you that much. So it's 10 times stronger, I can go out 10 times further. Instead of 10 kiloparsecs, I can go out to 100 kiloparsecs. That's the kind of distances it's allowing us to observe. That doesn't give us a lot more signals, but it does give us the potential to study. If we got a galactic supernova, we could say, wow, what's the level of asymmetry in the collapse, just based on the signal. The other asymmetry that we had in supernova was rotation. Again, if you had a reasonably strong rotating star, you can get the convection then is confined to the pole, so it makes an explosion along the axis, the rotation axis. But it also means that when you collapse and bounce, there's a quadrupole moment, and that quadrupole moment can make a signature. And so these are mildly rotating systems. I'm going to show a couple of movies where we actually people have simulated these rotating collapses. This is by Dimmelmeyer, Jose Font, and Ewald Müller. This one has a T over W, so kinetic energy over potential energy of 0.018. Here's the collapse, and as you watch, you'll see there it is. There's that quadrupole moment that's changing. That's the signal it produces. So it falls down and produces a signal that at that bounce you get a very strong signal, and then some succeeding bounces that then produce also a reasonably strong signal, all in the first few hundred milliseconds. So this is a relatively slow rotating system. We can look at another simulation by this group, same group, but now the rotational kinetic energy over potential energy is 0.04 instead of 0.018. And then we're using fairly simple models, polytropic index, so these are simple physics, but at some point it still has the features. So again, you see some nice quadrupole moments forming, and again, you get a signal at that bounce that you can see. Now, it changed quite a bit. The signal, the amplitude changed quite a bit from what the previous collapse as far as exactly its features. So it's going to have, they're going to have different features for different rotating systems, but the basic idea is you can get a much stronger signal because you have this bounce. You already have put in a quadrupole moment because of your rotation. And so for modest rotation rates, your signal can get up to even stronger than the asymmetric collapse. Here it's now 10, 15, 20 times 10 to the minus 22. So you're getting into the 2 times 10 to the minus 21 signal. So again, not getting you much further than 100 kiloparsecs away, but you start being able to, you will definitely be able to distinguish this kind of signal from an asymmetric collapse, and both of those from just a convection model. So at some point you can use the gravitational waves to probe the rotation rate of or the asymmetry of a collapsing core. And that's, I think, where we're at for gravitational waves if we do not have something more extreme going on. So if it's the models that we're expecting, the rotation rates are high enough to make a quadrupole moment, that can increase the signal by over a factor of 20 from a non-rotating case, but not enough to get us out to a megaparsec looking at these signals. There was some idea from Christian Ott that if we really did know the exact frequency, there is a potential to tune the detectors for LIGO and tune it in that frequency and be able to see further out. I don't think that's going to be done because I don't think we'll see if the core collapse community can agree on a frequency that they should be looking at. But I don't think our simulations have a agreed upon frequency. The core collapse community has just formed a committee to help give a single voice for gravitational waves. It's called One Voice, where we actually argue with ourselves before we present to the community. I did not get, we just started that just a week ago. So we will start trying to see if we can give a consistent picture on what we think the gravitational wave signal will be. I will tell you that I just saw a talk by Kei Kataki on gravitational wave signals where he was looking at the convection, and he had this very small feature that he was excited about because we could study details of the physics with this feature. And then he was going through the talk, and at some point someone asked, how far out can we see this? And that particular signal that he was focusing on could be seen out to 2 kiloparsecs. So that's not going to happen in my lifetime. I think if we have a supernova 2 kiloparsecs away in my lifetime, that would be amazing. So I think some of these things, some of this detection, I think we do have a good chance of eventually getting a galactic supernova. If I were Sanjay Reddy, who does neutrinos, he was convinced any day now it's time to have a galactic supernova. I think there's a good chance that we'll have a galactic supernova and see these signals and be able to constrain against these two, but that's about as far as it's going to go until we get the next generation gravitational wave telescope. So let's talk about the more fantastical events that will produce even bigger signals. One of these is if you can have bar modes. You can imagine having a speed up the star a little bit more, get it more rapidly rotating, and then you can form a bar mode in that collapse. Instead of just having some asymmetry, a quadrupole moment that's changing, you actually get a bar mode that can rotate around. Then you can calculate the period of that bar. It depends on the spin frequency to the 6th power. You could calculate the amplitude from that bar, and it's as the spin frequency to the squared power. So you can get a nice strong signal if I just keep on rotating the bar. But I was showing you models where the ratio of the rotational kinetic energy over the potential energy was 0.018 and 0.04. To get these secular instabilities to form bars or dynamical instabilities to form bars, you need either a value of 0.14 for secular instabilities and 0.27. So an order of magnitude higher than what I was showing in the previous calculations. If you do this, you can then get, this is what a bar mode instability looks like. Let's see if we can get this to play. And this kind of bar mode is going to produce much stronger gravitational waves. So it eventually gets rid of its angular momentum and becomes spherical. But if you can start off and produce a bar in the first place, you can make a strong signal. That signal, if we just say, I have this bar amplitude, it's going to survive for 100 coherent cycles, we can start seeing something out to 10 megaparsecs. So then if we could actually get any kind of event that is really rapidly rotating, T over W is above 0.14, we might be able to get a signal that can be seen out to 10 megaparsecs. This is the LIGO sensitivity, so advanced LIGO would be down here. It would even see, even if we only have one single cycle, it has a chance to see some bar mode instability. So you can, it looks like if we had bar modes, we would see them out to 10 megaparsecs, and that makes a big difference. So we can start to, if we start doing this, we will have calculations of these more extreme cases. Now, I will tell you that the rotation rates needed to produce bar modes are much higher than we've ever seen in any stellar evolution code or any scenario at the moment. But let's not even stop there. Let's go and rotate a little bit more rapidly. If we rotate it even more rapidly, you not only form a bar, but you fragment as you collapse. And for the life of me, I couldn't find it. I thought Thomas Janka or Ewald Müller and Max Ruffert had done some calculations of fragmentation, but I can't find them. But if you do fragment, then you essentially produce a binary. And in the case of these binaries, you have a very strong signal. It's like a binary neutron star emerging. And then you start being able to see the signal out to 100 megaparsecs, even 200 megaparsecs. So you can make really strong signals if you have a really rapidly rotating core when you collapse. And so, of course, we're going to at least look at these. The rotation rates this requires, I think it's almost already ruled out by the neutrino signal from 1987A, because it definitely changes how your neutrino signal looks when you get this kind of fast rotation, because the core does not collapse down to nuclear densities. It actually, the peak density at collapse is well less than about 10 to the 13, 10 to the 12 grams per centimeter cubed, instead of this 10 to the 14 grams per centimeter cubed that we see in normal collapse. But the advantage with these strong fragmentation signals is you can actually see the signal out to a Z of 5. So and that's even with normal LIGO. So if this actually occurred, we would start seeing it. The fact that we haven't seen it implies to us that probably you're not getting large coherent cycles for these fragmentation. Right? I don't know what this Z equals 5 is. Right? You can see these out. You should be able to see these out to a few hundred megaparsecs. So that's what you can do with collapse. The other place that people have looked at are in Rossby modes on the neutron star. So we know what, most people have an idea what Rossby modes are, even if they haven't heard of them. They're also called R modes. If you have ever looked at the modeling climate and its evolution, you can get you can get some undulation in the air between the cold and the warm air. It ends up forming cycles, something looking like the spot in Jupiter, where you get current cycles that start to rotate, and you'll get a rotating cycle that looks like it's evolving. It's moving across the planet, but as far as the jet stream is, it's moving in this direction in the jet stream. And so it's caused by the Coriolis force acting as a restoring force along the surface of your planet. So this is where Rossby modes were first proposed. The periods are in the same order of the star's rotation, so you have a rough idea of what the periods are. If you put this onto a neutron star, and imagine you're getting the same kind of Coriolis effect on a neutron star, you can get Rossby modes with periods in that millisecond time frame that would be easily detectable if they actually occurred in neutron stars, nearby neutron stars. Most of the focus on this has been on looking at Rossby modes in accreting neutron star systems, things like low mass X-ray binaries. There's a range of where the Rossby mode can be produced as a function of the period of the rotation period and the temperature of the neutron star. It depends a lot on things like viscosity in the star, and so there's a lot of uncertainties in it. One of the there's a whole set of people working on this, Niels Andersens, Kokoda, Arras, Watts. They've done a lot of work trying to understand the physics in the neutron star to model this. This is Niels Andersen. I point him out because he also is the author of children's books, the Professor Compressor thing. You can get it online. It actually, I think it costs something like $1 or 50 cents to buy this book online. So if you want to read a book by a R-mode physicist, here's your chance. The typical growth of the amplitude is that it starts off low, the amplitude grows, and then it starts to spin down the neutron star, and so you get a decrease in this, the amplitude. So it has some growth phase until the amplitude, the R-mode amplitude gets large, and then it gets weaker. So the interesting feature of R-modes is they actually feed on themselves. As they grow, so here's the toy picture of how R-modes grow. If you have a merry-go-round moving in one direction and a child running opposite, he's running along the merry-go-round, running the opposite direction of the merry-go-round, to the observer, he's spinning with the spin of the neutron star, because he's not going as fast as the merry-go-round. If he somehow gave up energy because he's not, he's spinning around this direction, if you slow down his energy, if you slow down that arm mode motion, you're actually speeding him up. If it makes it look like in your rest frame he's slowing down, that actually means he's speeding up in his run across the race, and that's what the arm mode actually feeds on itself and spins itself up. And so the arm mode amplitude increases quite quickly as it initially grows. Then the amplitude saturates, and that's when you get your signal starts to decay again. So for a neutron star that forms through the collapse of a massive star, it has fallback. Here's that amplitude. The amplitude grows, and then it saturates, and that's the amplitude during that period. These are different assumptions in the accretion rate. So here's the frequency of the spinning neutron star. It starts off spinning rapidly. The arm mode amplitude grows. It starts to decay. If you add some accretion, it can go back up again and make another signal, so you can have features like this. These are the kinds of features you expect with arm modes. This was assuming a very simple viscosity for the neutron star. What's happened since then is people have done more detailed viscosities for arm modes, and as they do those more detailed viscosities, they're finding that it's harder than we thought to produce arm modes. It may be that there's not that many conditions where arm modes are that strong in neutron stars. If that's the case, this is not going to be a strong signal. But you can see here in the amplitudes, they're around 10 to the minus 24, so they're still a ways from being detectable for any supernova that we're interested in. They're actually better with low mass X-ray binaries. We have some nearby low mass X-ray binaries where you might be able to detect them, and that's where most of the focus on arm modes has been. So here's the if you really up and decided to be really extreme on what you could do with arm modes, you could see it out to 10 megaparsec. But this required cheating in almost every way possible, and I don't think we're going to see that kind of arm mode signal in any real setting ever. So arm modes are probably not a likely detection, but they were at least one thing that we looked at. The last one, last kind of real source for gravitational waves from stellar collapse is a phase where you get when you first form a black hole, it has a metric associated with it, say it's in the Kerr rotating black hole metric. If you're accreting material onto it, you're shifting that metric. You're causing it to gain mass, you're causing it to spin up, and that shift in the metric causes it to ring. And so we actually see the ringing in the first signal we've seen where you had two black holes merge. This part here is where you're seeing the ringing of this newly formed black hole after you've merged two black holes. So you can also get that if you take a collapse of a star and then you accrete material onto it and look at how that can cause some ringing in the black hole. And so this is one option for making strong signals. The way you would really extremely, push an extreme in this kind of black hole ringing signal is to look at the most massive stars. So the most massive stars, 300 solar mass stars, when they collapse, they form a black hole. Their collapse, instead of collapsing down to a 10 to the 14 gram per centimeter cubed high density core, they actually collapse into a large proto-black hole. So this is the collapse of a massive star. This is about 50 solar masses in the core. Instead of that 1.4 solar mass in a normal collapsed core, this 300 solar mass star collapses to a 50 solar mass proto-black hole. Right now, the event horizon is still within that core, But as it gains mass, the event horizon appears, and this entire 50 solar masses collapses down to a black hole. The density of this 50 solar masses at this point is only about 10 to the 12 grams per centimeter cubed. So it doesn't collapse as deep in the potential because it has a much higher entropy than normal stars. But when it does collapse, it forms a black hole. It accretes like crazy onto it, so it's really being hit hard by material surrounding it, and that's going to produce the strongest signal from black hole ringing. So people have calculated, Scott Hughes calculated the signal for these high mass stars pushing the extreme. I think he was using 1,000 solar mass star in this case to see how strong the signals would be. And this is the LIGO band sensitivity. So remember, advanced LIGO is down here. Those, if you really push the signal to the top, you could get a signal that went to could see these stars out to high redshifts. However, this was having everything go in his favor. He was making the strongest signal. I think he was ringing it with a hammer that was almost the same mass as the 100 solar mass black hole that he formed. So he had this big black hole, and then he accreted half its mass again on top of it to see if he could make a strong signal. So in the extreme case, this is hard to see. If you then take it to the more realistic case, it's probably not going to be detectable. So the only thing that could save the black hole ringing is really, can we form some of these massive stars much closer to us than we believe at this time. So this is an alternative to trying to form signals. So I started out this talk talking about the normal signals, things like mixing, things like mild rotation, and then I went to more and more exotic objects just to try to make a stronger signal. The exotic objects are unlikely to actually exist, but if they did, we would have a much larger pool of gravitational wave sources. So the story is still this. We have this detector. I think I haven't gotten a latest update, and I will tell you the LIGO team seems to be hush-hush on where they're at, which implies not great work. It means they're still probably in this blue curve rather than the green curve, which is where they wanted to be at this point of sensitivity. So they have a design sensitivity. The way to see it is in kind of this 100 frequency range. They're at a value that's maybe a factor of 4 less sensitive than they want to eventually get to. So whatever they're detecting now, if they can get that sensitivity, they can go out a distance of a factor of 4 further. This gives you a 4 cubed increase when so it'd be 64 more objects. 64 times more objects when they get down to design specificity. So they're at the point that if they're detecting a couple black hole binaries now per science run, they should be detecting over 100 black hole binaries when they get to the design level, if the number of events is constant as a function of volume. So we can definitely expect a lot more black hole binaries as they get better design specificity. This is when they get down here is when they'll start detecting neutron star mergers. But in all cases, the kind of standard detection rate for gravitational waves from core collapse is limited to about 10, maybe 20 or 50 kiloparsecs. With this signal here, or up at this signal, maybe I can get it up to 500 kiloparsecs with this working at design, the design plan. But even that, getting to 500 parsecs for us, here's the Milky Way. This really just gets the local group. So we're not. Unlike the black hole binaries, where I go up by sensitivity of factor 4, I get 64 times more. Here, I do get more galaxies, but I'm only getting up to 10s of more galaxies, not a huge number of systems that will help us detect a lot of sources. So we still are essentially hoping for gravitational waves from core collapse, hoping for a galactic supernova. The advantage is if we get a galactic supernova, we will be able to tell the difference between these kind of signals that are produced just by pure mixing, or if there's rotation playing a role in the collapse. So there's a range of just conclude, there's a range of possibilities for gravitational wave detection in core collapse. The convection and the rotation, I think, are the most likely. So those are the ones that is the primary focus for scientists. We will be working in the next decade to get detailed convective signals and actually know exactly what the different signals from convection will tell us. The rotation signals, so we've shown in a couple examples of remnants, it doesn't look like rotation is really strong in most of our remnant studies. In the case of CAS-A, it looks like the explosion does not have a preferred axis. It has several lobes moving upward. That implies a fairly low rotation. If that's the case, this convection signal might be the strongest signal we see, and that would be interesting in any event. So if we get a galactic supernova, it'll tell us something about the rotation rate of stars at collapse. Another example is the 1987A supernova. It looks like it has a single lobe going in one direction. Again, it does not look like there's a strong bimodal jet, so not strong rotation. So the evidence right now is the rotation shouldn't be strong, but I think the gravitational waves are a more direct measurement of that than anything else we have. So that will allow us to constrain things. The problem with these low rotation progenitors is the signals that we're looking at. Even to detect them, we need them in the galaxy. And if we actually want to do more detailed science with them, we need them to be within a few kiloparsecs. So this is not a sure detection source, but it is one of the, we discussed radiation, getting photons out of supernova. We have lots of observations from supernova from the radiative light, but the problem with radiation is there's a lot of work we have to do to get from the photon observation of supernova down to understanding the core. In the case of gravitational waves, we get a direct probe of that core. It's just very hard to detect. And with that, I'll end. Tomorrow I'll talk about neutrinos. Thanks.
Chris, are there questions?
So you said that if we detect gravitational waves from core collapse due to these changes in quadrupole moment, so it will shed light on the mechanism of convection and rotation, but still 10 kiloparsec, as you said, it should be galactic supernovae. What is the probability? Because probably there are some other observations that will, let's say, faster shed light on the mechanism, on the things what happens inside the core collapse, faster than this gravitational wave detection. Because only 10 kiloparsec, I don't know how long we should wait.
So. There's a reason why I left gravitational waves and neutrinos for last, because they're very hard to detect. There's lots of things where you can do indirect. The data is through indirect measurements. We are understanding the engine. That's my big focus on the new star observations of the titanium is it really is a nice observation of what happened in the core, because we're seeing. We had a convective engine, the explosion happened, the titanium is produced down in that region where we had that convection. So it's produced down there, and by looking at the titanium distribution as it's moving out, especially because it's just moving out, a reverse shock hasn't hit it or anything, so it's just moving out, that's a nice probe of the central engine in itself. It's still not completely direct. the advantage of gravitational waves is it's a nice direct measurement. For the total rotation in a core, you're right. You can be looking at, if you could get some good pulsar spins at birth, that tells you more, that will tell you something about the spin as well. Gravitational waves are just another way of observing it. I mean, I think you're at some. I mean, you can push me where you want to push on this, but I'm not. I don't want to defend gravitational waves as something that's that great, and it has the problem that it has to be within 10 kiloparsecs. The strength is, if we do have a galactic supernova, we'll get a gravitational wave signal, we'll get a neutrino signal. Certainly combined, and we'll talk about this more tomorrow, combined, the neutrino and the gravitational wave signal provide some nice, it would be a different set of evidence that would make us feel better about the picture that we have. Just like the one neutrino detection we had evidence that supernova produced neutron stars, but actually seeing the neutrinos was a nice direct measurement of that neutron star formation. In the same way, the gravitational waves will be a nice direct information on that convective engine.
Yeah, I agree. Of course it would be, but the probability is quite low.
Yeah, don't say that in a gravitational wave meeting. I know this for a fact. They will not like you if you say it. From experience, I guess.
Well, even if it's low, I mean, it's totally new science.
Yeah.
It's worth investing for the future.
Oh yeah, I mean, and this is not why they're building they'll build the next generation gravitational wave detector. Initially supernova, well, okay, I tell you the full story. Initially supernova and mergers were both considered high ranking, and then a couple of us, me being the leader of it, said supernova are not going to be easy to detect. And then they realized the real science case for them are the binary mergers. And that's what's going to drive their science in the future, is this binary mergers. They know that supernova are going to be difficult to detect and be that rare event. And the worst part is, so you were saying, okay, they have to be 10 kiloparsecs. They do not yet have a duty cycle that's more than about 50% of the time for LIGO. So they could even they could have a galactic supernova go off and miss it. And that, you're one event and you miss it, that would make you sad. But it's well within possibility for them, at least at the current way they're running. Maybe when they get all the detectors running, they'll have 100% coverage at all times. But, at this point, they don't have the 100% coverage. But their science is driven by the binary mergers, which I think they're going to continue to detect a lot of these. I think you're going to see hundreds of black hole binaries when they get to the design specifics.
Another question? If not, let's proceed.